Hello, today we will be discussing about the Earth's internal heat and also magmatism. The objectives of these lessons are the following. Under the Earth's internal heat topic, you should be able to describe the chemical composition and temperature of the Earth's layer, explain the mantle convection as way of heat transfer, and recognize the importance of Earth's internal heat. Under magmatism, you should be able to describe the chemical composition of magma, differentiate the three types of magma, identify the process on how magma forms, and recognize the importance of magmatism. If you think about a volcano, you know Earth must be hot inside. The heat inside the Earth moves continents, builds mountains, and causes earthquakes. So where do you think does all this heat inside the Earth come from? Earth was hot when it formed. A lot of Earth's heat is left over from when our planet was formed 4.5 billion years ago. So Earth started out with a lot of heat. One of the sources of Earth's internal heat is accretionary heat. Gravity attracts planetesimals to the proto-Earth. The planetesimals accelerate on their journey, gaining a kinetic energy. As they strike the proto-Earth at a high speed, their kinetic energy is converted to thermal energy, which is heat. Aside from the accretionary heat, Earth makes some of its own heat. Earth keeps a nearly steady temperature because it makes heat in its interior. The process by which Earth makes heat is called radioactive decay. For example, uranium is a special kind of element because when it decays, heat is produced. It's this heat that keeps Earth from cooling off completely. Earth's core temperature is estimated to be around 5,000 to 7,000 degrees Celsius. That's about as heat as the surface of the sun, but vastly cooler than the sun's interior. Let us discuss the Earth's layers. Here is an image showing the thickness of the Earth's layers. We all know that the Earth is composed of the crust, the mantle, and the core. So let us discuss them one by one. There are two types of crust, the continental crust and the oceanic crust. The continental crust is the one with the solid surface, and the oceanic crust is the one that is covered with water, or the ocean. The crust has a thickness of 100 kilometers. Below the crust is the mantle. There are two layers of mantle, the upper mantle and the lower mantle. The upper mantle is about 670 kilometers deep from the surface of the Earth, and the lower mantle is about 2,900 kilometers. Below the mantle is the core. Also, there are two layers of the core, the outer core and the inner core. The outer core is also called the liquid core because it is in the form of liquid. And the inner core is a solid inner core. This is another image, and this shows the temperature of the Earth layers. So here, in this column, we see the layers. The second layer shows the depth, and the third one shows the temperature. The rocky crust, which is from 0 kilometer to 40 kilometers. The temperature ranges from 0 degrees Celsius to 870 degrees Celsius. If we go to the mantle, which includes the inner mantle, you will have to go a depth of 2,700 kilometers, and the temperature in that area will be about 3,700 degrees Celsius. The next layer is the molten outer core. Molten because it is in liquid form, and the temperature goes up to 4,300 degrees Celsius. And the inner core, which is the hottest part of the Earth, has a temperature of 7,200 degrees Celsius and has a depth of 6,378 kilometers. Let us discuss each layer one by one. The crust is less than 1% of Earth's mass. It is cold, thin, brittle outer shell made of rock. Next is the mantle. It is made up of solid rock and it is hot. It is composed of three parts: lithosphere, asthenosphere, and mesosphere. Let us talk about lithosphere and asthenosphere. Lithosphere is the crust and the upper mantle, which is about 100 kilometers thick. It is cold, rigid, and solid. However, asthenosphere is beneath the lithosphere, which is composed of the upper mantle, to a depth of 600 kilometers, which is soft, weak layer that is easily deformed. The mesosphere is the rest of the mantle. It is hotter, but the higher pressure keeps this layer more rigid, and this is high in viscosity. The core. The core has two parts, the outer core and the inner core. It is dense metallic center of the Earth. The outer core is the molten metal. It is made up of liquid iron. It is about 2,200 kilometers thick, and the temperature increases from 4,700 degrees Celsius. The pressure increases from 329 megapascal, and the density increases from 12.2 or 12.8 grams per cubic centimeter. The inner core is the solid metal. The solid inner core rotates faster within the outer molten core. So you see, as we discussed, the hottest part of the Earth is in the core. So if you are wondering, how is heat transferred from the core to the other parts or other layers of the Earth? Heat flows in two different ways within the Earth. It is through conduction, and the other one is through convection. Conduction is heat transferred through rapid collision of atoms. Heat flows from warmer to cooler places until all are at the same temperature. The mantle is hot mostly because of heat conducted from the core. Convection. The movement caused within a fluid by the tendency of hotter and therefore less dense material to rise, and colder, denser material to sink under the influence of gravity, which consequently results in transfer of heat. This is an image how heat is transferred through convection. Here in the core is the hottest temperature. The hot temperature goes upward and the colder temperature in this part will go down. And this part will become hotter. Therefore, the hotter temperature in this area will still travel to the crust. And then the original temperature in the crust will travel downward because it is colder than the temperature that comes from the mantle. So this is how convection works. To sum up our topic, Earth's internal heat, the Earth is composed of radioactive elements like uranium and metals like iron and nickel. And this is one of the sources of the Earth's internal heat. Heat travels from the hottest portion, which is the core, to the mantle and to the crust. Now, I am going to leave you with one question. What is the importance of the Earth's internal heat? Please make a short explanation and discussion about this topic and leave it on our Google Classroom. Our second topic is about magmatism. Magmatism is the result of the transfer of heat from the core to the other parts of the Earth. What is magma? Magma is a molten and semi-molten rock mixture found under the surface of the Earth. This mixture is usually made up of four parts: a hot liquid base called the melt, minerals crystallized by the melt, the solid rocks incorporated into the melt from the surrounding confines, and the dissolved gases. When magma is ejected by a volcano or other vent, the material is called lava. Magma that has cooled into a solid is called igneous rock. Magma is extremely hot, between 700 degrees to 1,300 degrees Celsius. This heat makes magma a very fluid and dynamic substance, able to create new landforms and engage physical and chemical transformations in a variety of different environments. Magmas can vary widely in composition, but in general, they are made up of only 8 elements. In order of importance, the oxygen, silicon, aluminum, iron, calcium, sodium, magnesium, and potassium. Oxygen, the modern element in magma, comprises a little less than half of all, followed by silicon at just over 1/4. The remaining elements make up the other 1/4. Magmas derived from the crustal material are dominated by oxygen, silicon, aluminum, sodium, and potassium. The compositions of magma depends on the rock it has formed from and the conditions of that melting. Magmas derived from the mantle have higher levels of iron, magnesium, and calcium, but they are still likely to be dominated by oxygen and silicon. All magmas have varying proportions of elements such as hydrogen, carbon, and sulfur, which are converted into gases like water vapor, carbon dioxide, and hydrogen sulfide as the magma cools. This pie chart shows the composition of magma. So if you see, oxygen has almost half of the pie, and almost a quarter is silicon, and the other quarter is composed of aluminum, iron, calcium, sodium, potassium, magnesium, and other elements. Here are the types of magma. They are classified as basaltic, andesitic, and rhyolitic. Each of them has different mineral composition, gas content, temperature, and viscosity. Let us discuss the composition of magma per type. Basaltic magma contains 45% to 55% of silicon dioxide. It is high in iron, magnesium, calcium, but low in potassium and sodium. The andesitic magma, composed of 55% to 65% of silicon dioxide with intermediate amount of iron, magnesium, calcium, sodium, and potassium. However, the rhyolitic magma is consists of 65% to 75% of silicon dioxide with low amount of iron, magnesium, calcium, but high amount in potassium and sodium. At depth in the earth, nearly all magmas contain gas dissolved in the liquid, but the gas forms separate vapor phase when pressure is decreased as magma rises toward the surface. This is like carbonated beverages, which are bottled at high pressure. The high pressure keeps the gas in the solution in the liquid, but when the pressure is decreased, like when you open a can or bottle, the gas comes out from the solution and forms a separate gas phase that you see as bubbles. Gas gives magmas their explosive character because volume of gas expands as pressure is reduced. The composition of gases in magma are mostly water vapor with some carbon dioxide with minor amounts of sulfur, chlorine, and fluorine gases. The amount of gas in magma is also related to the chemical composition of the magma. Rhyolitic magmas usually have higher dissolved gas content than basaltic magmas. The temperature of magmas is difficult to measure due to the danger involved, but laboratory measurement and limited field observation indicate that the eruption temperature of various magma is as follows in degrees Celsius. Basaltic magma is from about 1000 to 1200 degrees Celsius. Andesitic magma is about 800 to 1000 degrees Celsius, and rhyolitic magma is about 650 to 800 degrees Celsius in temperature. The viscosity of magma is the resistance to flow. Viscosity depends primarily on the composition of the magma and temperature. The higher silica content magmas have higher viscosity than lower silica content magmas. Viscosity increases with increasing silica concentration in the magma. Lower temperature magmas have higher viscosities than the higher temperature magmas. Viscosity decreases with increasing temperature of the magma. Basaltic magma tend to be fairly fluid, but their viscosity is still 10,000 to 100,000 times more viscous than water. Rhyolitic magmas tend to have higher viscosity ranging between 1 million and 100 million times more viscous than water. Viscosity is an important property in determining the eruptive behavior of magma. This table shows the summary of properties of magma, depending on the magma type, what solid rock it can form, the chemical composition, temperature, viscosity, and gas content. But how is magma formed? Earth is divided into three general layers, as we have studied the core, the mantle, and the crust. Magma originates in the lower part of the Earth's crust and in the upper portion of the mantle. Most of the mantle and crust are solid, so the presence of magma is crucial to understanding the geology and morphology of the mantle. Differences in temperature, pressure, and structural formation in the mantle and the crust cause magma to form in different ways. So let us discuss the ways how magma is formed. First is decompression melting. Decompression melting involves the upward movement of Earth's mostly solid mantle. This hot material rises to an area of lower pressure through the process of convection. Areas of lower pressure always have a lower melting point than areas of high pressure. This reduction in overlying pressure or decompression enables the mantle rock to melt and form magma. Decompression melting often occurs at divergent boundaries where tectonic plates separate. The rifting movement causes the buoyant magma below to rise and fill the space of lower pressure. The rock then cools down into new crust. Decompression melting occurs at mantle plumes, columns of hot rock that rise from Earth's high-pressure core to its lower-pressure crust. When located beneath the ocean, these plumes, also known as hotspots, push magma onto the seafloor. These volcanic mounds can grow into volcanic islands over millions of years of activity. Under normal conditions, the temperature in the Earth, shown by the geothermal gradient, is lower than the beginning of melting of the mantle. Thus, for the mantle to melt, there must be a mechanism to raise the geothermal gradient. One such mechanism is convection, wherein hot mantle material rises to lower pressure or depth, carrying its heat. If the raised geothermal gradient becomes higher than the initial melting temperature at any pressure, then a partial melt will form. Liquid from this portion melt can be separated from the remaining crystals because, in general, liquids have lower density than solids. Basaltic magma appear to originate in this way. A quelling mantle appears to occur beneath oceanic ridges, at hot spots, and beneath continental rift valleys. Thus, generation of magma in these three environments is likely caused by decompression melting. This is an image where decompression melting occurs in this part and in this part. Transfer of heat. Magma can also be created when hot liquid rock intrudes into Earth's cold crust. As the liquid rock solidifies, it loses its heat to the surrounding crust. Much like hot fudge being poured over cold ice cream, this transfer of heat is able to melt the surrounding rock into magma. Transfer of heat often happens at convergent boundaries where tectonic plates are crashing together. As the denser tectonic plate subducts or sinks below, or the less dense tectonic plate or hot rock from below can intrude into the colder plate above. This process transfers heat and creates magma. Over millions of years, the magma in this subduction zone can create a series of active volcanoes known as volcanic arcs. When magmas that were generated by some other mechanism intrude into cold crust, they bring with them heat. Upon solidification, they lose this heat and transfer it to the surrounding crust. Repeated intrusion can transfer enough heat to increase the local geothermal gradient and cause melting of the surrounding rock to generate new magmas. Rhyolitic magma can also be produced by changing the chemical composition of basaltic. Another way magma is formed is by flux melting. Flux melting occurs when water or carbon dioxide are added to rock. These compounds cause the rock to melt at lower temperatures. This creates magma in places where it originally maintained a solid structure. Much like heat transfer, flux melting also occurs around subduction zones. In this case, water overlying the subducting seafloor would lower the melting temperature of the mantle, generating magma that rises to the surface. If water or carbon dioxide is added to rock, the melting temperature is lowered. If the addition of water or carbon dioxide takes place deep in the earth where the temperature is already high, the lowering of temperature could cause the rock to partially melt to generate. One place where water could be introduced is at subduction zones. Here, water present in the pore spaces of the subducting seafloor or water present in minerals like hornblende, biotite, or clay materials would be released by the rising temperature and then moved onto the overlying mantle. Introduction of this water in the mantle would then lower the melting temperature of the mantle to generate partial melts, which could then separate from the solid mantle and rise toward the surface. This is an image where flux melting could occur in this area where water could be added to the rocks, and also here. This is an image of a geothermal power plant in Iceland. In 2009, the Icelandic deep drilling project created a well that uses magma to generate geothermal energy. Normally, geothermal energy is created by pumping water into hot volcanic bedrock, creating steam that is then harnessed to generate electricity. While normal geothermal sources averages around 60 degrees to 80 degrees Celsius, the magma well steam reached a record-breaking temperature of 450 degrees Celsius. This huge increase in temperature allowed just one magma well to generate roughly 36 megawatts of electricity, powering 36,000 homes. In comparison, one single wind turbine generates between 1 to 3 megawatts. To summarize our topic on magmatism, magma is composed of oxygen, silicon, aluminum, iron, magnesium, calcium, sodium, potassium, and others. There are three types of magma: basaltic, andesitic, and rhyolitic. Magma is formed through the following: decompression melting, transfer of heat, and flux melting. Now, I am going to give you another question. How can magmatism impact our lives? And you have to leave your answers on our Google Classroom. Thank you and good luck.